Well, I got the warning on Zoom, so.
It's going farther this time. There it is. Okay, we are live. Sorry for the delay to everyone out there, but welcome to Climate Chat. I'm your host, Dan Miller, and today we have a very special guest, Rob Jackson, who is a climate scientist at Stanford, and he does a lot of other things, so we're going to hear about that. But before we get into that, I just want a few programming notes. There will be no talk, no climate chat next Sunday because I'll be attending my nephew's wedding. Can't do it then. The week after, September 1st, we're going to have Carrie Browder, who's director of Project Frame, which is a nonprofit that helps investors to evaluate the quality of climate solution companies. That'll be very interesting. And the week after that, September 8th, we have Catherine Hayhoe, a well-known climate scientist that spends a lot of time reaching out to the public. It would be a great discussion. One other small programming note, happy birthday to Leon Simons. And now, welcome, Rob. I'm going to give Rob's a brief bio here. Rob Jackson is the chair of the Global Carbon Project, a senior fellow at Stanford's Woods Institute for the Environment and Precourt Institute for Energy, and a professor of earth science at Stanford University, my alma mater, by the way. Though through global scientific leadership and groundbreaking research, communications, and policy activities, Rob's work has reduced millions of tons of greenhouse gas emissions and improved human health, safety, and air and water quality. One of the top 5 most cited climate and environmental scientists in the world, by the way, congratulations, amazing. He has authored more than 400 peer-reviewed publications, and his writings have appeared in many outlets, including New York Times, Scientific American, and the Washington Post. Welcome, Rob. Great to have you here. And maybe you could just start off and tell us, what is the Global Carbon Project?
First of all, thanks for having me, and thank you everyone online. The Global Carbon Project is a group of independent scientists. We have thousands of scientists who contribute to our tracking, if you will, of greenhouse gas emissions. We measure emissions from human sources, so fossil fuel use, buildings, agriculture, and we compare those emissions to natural sources. In the case of methane, a gas that I study, we measure wetlands. I work in the Amazon as well as in homes and buildings and pipelines. So in the Global Carbon Project, we try to put all of these pieces together from the ground up, literally, in a bottom-up approach, and from the atmosphere down using satellites and isotopes and different tools. And we assemble budgets. How much of a greenhouse gas is coming out? How much of it contributes to a rise in the atmospheric concentration? And how much of it is human-caused?
Okay. So on the human cause side, do you have a top-level number, like 50 gigatons a year is the number I've heard? I mean, is there a number you quote, or do you just say these? I guess it's usually CO2 emissions is the one that's usually quoted.
Probably our most widely used product is our global carbon budget, which is led by Pierre Friedlingstein in Exeter. And from fossil fuel emissions, it's close to 40 billion tons of carbon dioxide pollution a year. It's a little more than that when you take into account land use, deforestation, and things. But yeah, roughly 40 billion a year for 40 billion tons a year for CO2. And methane, it's about 300 to 400 million tons a year. But the methane cycle is far more perturbed or dominated by human activities. More than 60% of all methane emissions in the world comes from things that we do.
Right. And by the way, we're going to really dig into that because that's a key. And we actually had a show last week where we were with Leon Simons and Elliot Jacobson, where we were talking about CO2e and how do you calculate that for methane, and super important stuff. But you have a new book, Into a Clear Blue Sky. And I have to tell you, we interview lots of climate scientists here, but your message is actually far more optimistic than many climate scientists, because you say we can actually do something now to really make a difference. Could you just give us like an overview of the book?
I think of it as a repair manual for the planet, an approach personally as well as for other people in a journey from climate despair to climate repair. I focus on methane because methane is a powerful greenhouse gas. It's also the greenhouse gas that, if we cut emissions today, could reduce temperatures in the next decade or two. It's the only one for which we could do that. So it's a very potent lever for reducing temperatures today. And I interview everything from individuals who are making a difference with their own actions to the CEOs of different companies, steel, energy, transportation. And I went looking for hope. And like all people, I don't know what to do about climate change. The emissions keep going up. We haven't turned the corner yet, and we know in the scientific community we understand the consequences of these unchecked emissions and have to do something about it. And I wanted to try and help people see that we have the tools and that there's a path forward to action.
But your approach, as I understand it, is the focus on methane and the fact that methane doesn't last in the atmosphere very long. If we stop emitting it, then after 10, 20 years, then the human part of it will basically disappear. Is that right? Or do you also talk about active measures? For example, we have carbon dioxide removal systems like direct air capture, and there are some methane destruction systems as well. So can you tell us, is it mostly stopping the emissions or other more active measures to remove emissions?
I do talk about both, but stopping emissions is by far the most important thing that we can do. And as I've already mentioned, methane emissions are dominated by agriculture and energy activities from things people do. And I use the concept of restoration in the book as well. And by restoration for a greenhouse gas, I mean restoring its concentrations to pre-industrial levels.
Right.
And methane is the only dominant or major greenhouse gas for which we could do that in the lifetime of anyone on this call. And that's my dream to see that happen. And we would have to eliminate almost all methane emissions for that to occur. But by doing so, we'd save 0.5 degree C of warming. And there's no other gas that gives us such immediate power, if you will.
So, well, I have so many questions for you about. So let's address one of the questions we had last week was, you hear about how more powerful methane is than CO2, and you very often hear it's like 30 times more powerful, which really is over this 100-year period. Or you might hear it's 86 times more powerful, which is like over 20 years. But while it's in the atmosphere, it's a lot more than that. So when methane is in the atmosphere, what is its multiplier? It's GWP1 or
So at the second that it's emitted, methane is about 120 times more powerful ton for ton than carbon dioxide. The longer you go, the less, the more that number shrinks. So at about 20 years, it's 80 or so, times more powerful, 80 to 90. And then at a century time scale, it's about 30 times more powerful. But in a century, effectively every pound of methane that you emitted a century ago is gone from the atmosphere. So at that point, you're still getting warming from carbon dioxide and getting very little warming from the methane release.
So but if you're going to, I'm sorry, if you're going to do a CO2e, I assume you would take the amount.
Can others?
Oh, there you go. Okay, you just froze for a second, at least on mine.
No, Dan, it was you. You froze.
Okay. So
yeah. Are you
sorry, keep going.
Okay, sorry.
You were talking about CO2e or something like that.
I'm just asking you to calculate CO2e. Do you just multiply the extra CO2 that's in the atmosphere due to humans and multiply it times 120? Because that's the warming we're getting at this moment, right? The 20 years and 100 years is to figure out which is worse, a ton of CO2 or X tons of methane, that kind of thing.
Well, the closer to the time frame that you're concerned about, the more important methane is, and the longer time frame, the more important carbon dioxide is. And there are 1 trillion extra tons of carbon dioxide floating around in the atmosphere, and that much of that extra CO2 will still be there in thousands of years. It makes it very, very different than methane, because it's one reason there's so much emphasis on carbon dioxide removal, because if you had a magic wand and could eliminate all fossil CO2 emissions today, that 1 trillion tons would still be floating around in the air and warming the earth for millennia. And if you had a magic wand for methane, and you could eliminate ag and fossil fuel energy related emissions. As I said a minute ago, you could see the atmosphere restored for methane within a couple of decades.
So let's go into each one. So agriculture, what are the main sources of methane in the agriculture sector?
The two main sources from agriculture are cows, ruminants and their waste, their manure, and a lesser amount from rice farming. Methane is formed biologically in low oxygen, often very wet environments. It's formed its largest natural sources in wetlands. So a wetland is very similar in environment to a rice paddy rice paddies are typically flooded. And it's actually pretty similar to what's happening in a cow's gut, right? You have a low oxygen, wet environment sloshing around, and the microbes in that environment generate methane. So think of cows and rice are the dominant sources, and those sources are bigger than all energy-based or fossil fuel sources, which also
Really?
which also makes it very different from some other gases we study.
I thought fracking. Well, I interviewed Bob Howarth like 3 years ago, by the way, a long time ago. We talked about this. Back then, he was saying that the growth in methane, as opposed to maybe what the total that was coming mostly from fracking. Back then too, it was a little while ago too, and with fracking was like zooming and. But so wow, that's amazing. So how would you propose getting rid of rice and cow methane in the next,
but there are several ways, and of course, anytime we're talking about food production, I have to acknowledge that there are people in the world who don't have enough protein. So it's one thing for me to talk about eating less beef, and I don't eat beef anymore. But it's one thing for a wealthy person with enough protein in our lives to reduce our beef or meat consumption. It's another thing for a person in Africa who might not have enough protein in their lives. And same for rice. There are people who don't have enough to eat, and the rules should be different for them. But what we can do for methane around food and agriculture, we can individually eat less beef and dairy. And that's probably the most important thing that we can do agriculturally. There are people and companies, though, trying to reduce methane emissions cow by cow. So you can think of lowering the number of 1 billion plus cows on Earth, and then however many cows are left, we need to eliminate methane emissions from them. And the best technologies emerging for that are through feed additives, very small amounts of things like algae and different chemicals. There have been some new products approved, even in the US, a product called Bovaer that cuts emissions about 1/3 or so. And some of these algae look like they'll cut 80 or 90% of emissions. The problem with them is that we feed cows in a dairy or in a feedlot on a daily basis. But if you're a Wyoming or a California rancher, you don't feed your cows day by day. So it's hard to touch 1 billion cows. And that's why reducing the number of cows is so important. Wow. And then just briefly on the side for rice, the dominant way people are trying to lower methane emissions from rice paddies is to lower the water levels, to stop flooding them all the time, to periodically let them dry down, and that knocks back the microbial activity that generates methane. Oh. But that's a practice change as well as a cultural change. People in Asia flood fields for pest control, and because it's the way they've always done it. So food production is challenging.
Okay. And how about on the energy side? What are the main sources of methane emissions?
Well, the main source of methane emissions on the energy side is from fossil fuel extraction and use. That's pretty much it. From coal, oil and gas extraction, every oil and gas well we drill tends to leak a little methane into the air. I've studied pipelines, and we've did the first studies of emissions along pipelines, mapping leaks. I drove block by block cities in Boston and DC and found thousands of gas leaks going to the air. We do the same thing in homes too, from stoves, water heaters, and furnaces. So every time we burn a fossil fuel, there's an associated emission of methane to the atmosphere, all the way from where that fossil fuel came from in an oil and gas field, through the pipelines, all the way to our homes or power plants. So the first thing we can do is to use less or stop using fossil fuels.
So, by the way, I read long ago about your work in Boston mapping. I didn't know it was you at the time, but I was really fascinated. I heard that you found some areas that were like explosive levels of natural gas were leaking out of the ground because of these old pipes that are taking natural gas to all the homes.
Yeah, that's right. And I would also want to credit my colleague Nathan Phillips at Boston University, with whom I did that work. In Washington, D.C., we mapped 6,000 leaks, mostly finding them in older neighborhoods. There are cast iron pipelines that were laid, not that long after the Civil War, more than 100 years ago. Not surprisingly, those pipelines tend to leak. We called in a dozen explosive concentrations to the utility, went back and mapped them 6 months or a year later, and I think 9 of the 12 were still explosive, which was a shock to us.
Wow. So one of the big this was controversial a while ago that Bob Howarth came up with. He was saying that if you take the percentage of natural gas that we produce and you say what percentage is fugitive emissions, these leaks, coming out of the pipes or upstream, and he said it was actually several percent, and the industry was saying like 0.5% or something. What is the, I guess, agreed, or what do you think the value for the fugitive emissions is today?
Yeah, it's a great question. It's a hard question to answer because it depends whether you're talking about just the US, other countries, whether you're talking about just oil fields or natural gas fields. The highest emissions appear to come from basins like the Permian in Texas that get so much attention, the Bakken. These are fields that focus on oil production. And when you're getting $100 a barrel for oil, getting a couple dollars, for a bit of natural gas is not really a priority for these companies. So those fields tend to have the highest emissions, and estimates are as high as 3, 5, even 10% from a recent aircraft-based study in the Permian. Wow. I mean, shockingly high in many cases, and far higher than the industry says they are.
And so what you have to do is now so this is why people think, and the United States and international bodies all assume that when you switch from coal to natural gas, that you've lowered your cut your emissions in half, because the CO2 per kilowatt hour of energy produced in a natural gas plant is about half what it is in a coal plant. But with what you just said, if you throw in the fugitive emissions, plus the fact that you actually don't have dirty smoke to reflect the sun anymore from coal, I've heard when you switch from coal to natural gas, you've actually immediately increased global temperatures because of those two factors. Fugitive emissions at 120x, okay, over 20 years, it's 86, and plus you don't get the reflectivity of the aerosols. So is that accurate?
It may be. I'm not sure that that's universally true, that I would be ready to say that. First of all, gas is a better fuel than coal. Coal is a 19th century dirty.
It's terrible, yes.
Pollution from coal and cars kills 100,000 Americans a year still, even though our air is better. So there are other reasons to get rid of coal beyond climate, and particulate pollution is one of them. Having said that, gas is not clean. It's cleaner than coal in terms of particulate pollution. It's better than coal in terms of carbon dioxide emissions. Coal mining releases methane to the air too. So it isn't just the methane that comes from natural gas extraction. You have to also take into account the methane that's released into the air from coal mines, and deep coal mines in particular release quite a bit of methane. So I'm not ready to say that universally methane or natural gas is worse than coal for climate, and it's certainly better for health than coal. But it's not a long-term solution that helps us zero out greenhouse gas emissions. So we do have to, to look to a future where either we're sequestering all of our fossil fuel pollution, or we've transitioned to cleaner electricity from green sources.
So that's your approach then for the energy side, is to, first of all, obviously transition to renewables. But what about like sealing up all the leaks, taking those emissions from the Permian and flaring it instead of letting it leak out? What's your approach to getting energy sector methane emissions, as low as possible?
Yeah, I think there are a couple of things we have to do. We have infrastructure on the ground, and no one likes to take a perfectly good oil well out of operation that's still producing. No one likes to take a perfectly good stove out of a home that's still working, that's run by gas. So we have to clean up the infrastructure that we have. So I support those activities. Just on Friday, I was lucky to see the launch of the new Carbon Mapper satellite down at Vandenberg Space Force Base, and watch that blow up into not blow up, but rise into the air, and the amazing rocket, SpaceX rocket, come down and land like a pencil. I'm excited about those satellites. They will help us detect super emitters in oil and gas fields, wastewater treatment plants, landfills, all over the world too. There'll be nowhere to hide. It's true in the US, but it'll let us see into Russia, China, places we can't fly airplanes and understand. So we do have to clean up the infrastructure that we have, but we have to talk about an endpoint to fossil fuel use. Does that endpoint, when is that endpoint? If you think about gas distribution, we have pipelines that run to our homes. How do you turn off a gas pipeline to a street if there's one home that's still using gas on that street? And utilities are struggling with these issues. There are some utilities, like here in California, my utility PG&E, that in some cases are paying people to electrify their homes to keep them from having to replace expensive pipelines. So we really have to think hard about how we transition and end fossil fuel use. It's not simple.
Okay. Yeah, I personally think the government should just pay to have all the heat pumps put in and all that kind of stuff. It will be cheaper in the long run than, the slow transition, because the cost of fossil fuels, as we're learning with climate change, is enormous, and we have to work as quickly as we can. So you talked about agriculture, you talked about energy sector emissions. There's another set of emissions that lots and lots of people are worried about, and I'll just call them Earth emissions. This is melting permafrost, clathrate, which are sort of ice-covered methane deep at the coastal, well, deep in the ocean, and not always deep. Sometimes the Arctic Sea, for example, is not deep. And there's a fear that this methane can start releasing and overwhelm our human emissions. Can you just give us your take on, I guess, where we are right now in terms of those emissions versus our human emissions, and where you see it maybe 2050 or something like that?
Yeah, I can. In fact, the last chapter of my book takes place in the Amazon, intotheclear.com. It takes place in the Amazon, and we're concerned about tropical wetlands because tropical wetlands are the largest natural source of methane emissions to the air. Again, they're wet, they're low oxygen when they're flooded, they're warm temperatures, so microbes are very active. And we're working with partners in Peru and Brazil and French Guiana to establish towers and monitoring networks across the Amazon. The tropics are the least understood ecosystem on Earth. They're hard to reach and hard to work in. So we're trying to understand what emissions are today, and we expect emissions to go up in the future from tropical wetlands as temperatures warm, all else being equal, because microbes grow faster in warmer temperatures. So we're very concerned about accelerated natural emissions, if you will, or emissions from natural sources because of climate change. You mentioned the Arctic, and the permafrost is another example. There's almost half as much carbon locked away in permafrost as there is in the entire atmosphere. So if we
I heard it's twice as much. There's twice as much carbon in the permafrost. That's what I've heard, than that exists in the entire atmosphere. Is it you say it's half as much? Or
well, it depends. So we published a paper just a couple of years ago just for permafrost. It's about 400 billion tons. But if you include all of Arctic soils, across the area, there's a lot of organic. It's an organic rich soil matrix. So then there's far more than that. Either way,
it's a lot.
Yeah,
you
take a lot of carbon relative to what's in the atmosphere. You thaw it out, you warm it up, microbes start to chew at carbon that was previously inaccessible to them, and bad things happen. You either produce carbon dioxide to the air, which is bad, or if it's a waterlogged system, you produce a lot of that carbon as methane, which is or could be catastrophic. So we've got our eye on tropical wetlands, Arctic systems, and if these systems start to increase, there's not evidence yet, in my opinion, that they've accelerated a lot. We're starting to see some hints in places like the Congo that emissions may be going up. When these start to go up, there is right now literally nothing we can do. We have no tools, no companies for dealing with these extra emissions. I mean, we're just stuck with them. So we're setting in motion things that we can't control.
What percent? I mean, let's count the permafrost, the Earth emissions due to rising temperatures as being human caused, right? It's not, they weren't going to happen except for the things we've done. Today, are they 10 or 20% of the cows and the energy, or Is there a feeling for how big a problem it is now?
Well, in terms of their overall emissions, wetlands and freshwater systems are larger than the energy-based. The natural emissions are larger than either the energy-based or the agricultural emissions, or close to the ag emissions. The extra that's coming, there's no evidence for extra methane coming from the Arctic yet. There are
Really?
Well, not on a global basis. When you look at the concentrations of the atmosphere up there, there are clear places where you're seeing bubbles. The East Siberian Sea is
Right.
a well-studied example. There are things happening, but we don't see the consequences of that propagated across the Arctic as a whole. And I say that based on atmospheric concentrations, tower-based measurements. That is not to say that we shouldn't be worrying about this. We should desperately be worrying about these systems, but there's not runaway methane release happening in the Arctic yet, in my opinion. Same is true in the tropics. We're starting to see hints of increases, and it's deeply troubling.
Is there a feeling, because as you know, a lot of people involved in climate, this is the thing that kind of blows their mind and gets them losing sleep. And is there a feeling of the time frame? Is it a decade, a century? I mean, when this could go from being a small thing to being a huge thing, or could it ramp up really quickly past some threshold in temperature, for example?
Great question. And there's a lot of work done on tipping points, and both of these systems, Arctic thawing and Amazon and tropical wetlands are tipping points. I don't think there's no clear number. It's not like a shelf where we cross, there's 1 ton of extra pollution that pushes us over the edge. That may be the case, but we don't know where that threshold is. But I would say certainly within the next 10 or 20 years, if we continue to emit as we are now, we'll start to see clear evidence that these systems are changing. Tropics is a little more complicated because it isn't just a matter of temperature. There are parts of the tropics that are getting drier, parts of the tropics that are getting wetter. The combination of wetter and warmer is deadly for methane, deadly in terms of higher emissions. But if you get warmer temperatures but drier conditions, you don't necessarily get higher methane emissions in that case, because the microbes need that low oxygen environment,
right,
waterlogged environment. But the Arctic, you warm the Arctic and bad things happen. You melt ice, you lock away thousands of years worth of basically plant growth that's been that's been stored underground, and no one wants that.
So you mentioned earlier that if we can get a hold of our methane emissions and get them really low, we could save 0.5 degree of warming. And this could happen, if you did it tomorrow, it would happen in like 20 years, which would be a fantastic thing. But when you're getting rid of these emissions, assuming you're doing it by switching to renewable energy, let's say, plus the cows, you deal with that somehow. But when you get rid of the fossil fuel emissions, you're also getting rid of the aerosols that are currently cooling the Earth. And I've always heard when we get to zero emissions, temperatures stabilize because, and there's 4 factors, and one of them is your factor, but the 4 factors are the warming in the pipeline, the Earth energy imbalance, which would keep the Earth warming after we stop emissions, is offset by the fact that the oceans will continue to take up CO2 as if we were still emitting, right? The same amount they did last year. It doesn't know what our yearly emissions is. It only knows what the total cumulative emissions are. And so that would lower CO2, and that would tend to cancel out. I don't know how much exactly. But then when it comes to methane, then we, of course, get rid of methane, short-term greenhouse gases like methane, and that would cool the Earth, but that would be offset by aerosols going away, which are roughly the same amount. I mean, aerosols might be more, but so what do you think of that? And do you consider solar radiation management, solar geoengineering as being a solution to make sure that the loss of aerosols doesn't counter the methane cooling?
Yeah, really important and very difficult question. I don't study solar radiation management. Blasting dust into the stratosphere to mimic a volcano to block sunlight. I don't do research on that topic myself.
Okay. We had David Keith on a few weeks ago.
I personally, but I do know fair bit about it, and I am not everyone will have climate solutions they don't like to solve the climate problem, and that includes energy generation and such. I am not ready to embrace solar radiation management, not because I don't think we can do it technologically. I think we can. I think it's one of the cheapest things we could do. I'm concerned about it because it does nothing to stop ocean acidification. It may buy us where CO2 continues to go into the oceans and acidify the water. It could buy us some time. I'm just not convinced we ever get a social contract internationally to do this. Imagine in the US telling Congress, all right, we're going to cede the control of the world's climate to the United Nations. Like, how is that going to go down in our current Congress? I have trouble seeing the social consensus needed to govern global temperatures in the way that this would require. And once we start, you can't stop, right? If you do this for 50 years and you stop abruptly, temperature does this. As soon as the aerosols fall out of the sky.
Termination shock.
Yeah, the termination problem or shock. So I am not personally ready to embrace solar radiation management yet. I still think we need to focus on cutting emissions now, as soon as we can.
But so given that, though, of course, we are doing solar radiation management on a massive scale today. We're doing it accidentally by burning coal and ships and these things, and it's cooling the Earth by at least the same amount as methane. Recent work, Jim Hansen, they're suggesting it's actually more than you think, because it's really not just the aerosols, it's how they seed the clouds and things like that. And then the recent drop in shipping emissions due to new regulations has caused the temperature to spike, at least according to Jim Hansen, Leon Simons, and others. So what I said, though, is then correct, right? So we cut methane emissions and we save this 0.5 degree of cooling, but we're also going to get that back as we cut our aerosols, because at the same time we're cutting, I assume the same time we're cutting methane emissions, we're also cutting coal and other kinds of emissions that are methane. The interesting thing is methane doesn't create the aerosols, right? To start with, but coal does, and it's, as you said, it's way worse. We better cut our coal and other pollution that are killing 8 million people a year, right? So is it true that we're not going to end up lowering the temperature? We're going to end up stabilizing the temperature if we do that?
I don't think that's necessarily true, or I'm not sure exactly what the numbers are, and it depends whether we're talking about eliminating all fossil fuel use. First of all, let me say, I don't think we're not doing solar radiation management today. We're filling the atmosphere with particulates and pollution that do have important aerosol interactions, but that's way down here, and solar radiation management is way up here in the stratosphere.
Right. So you need a lot less.
There's almost nothing that we do that loads the stratosphere with pollution in terms of particulates, because it just doesn't get high enough.
Yeah, I agree.
So, but your point's a good one. We have to, we just have to. It's part of the solution set. We have to work extra hard to take into account this the cooling that's coming from aerosols. Just like we don't acknowledge the extra uptake of carbon dioxide that the land and oceans are giving us, where essentially every 2 tons of pollution we emit to the air, only 1 ton stays in the air. And when we start to see concentrations come down, we get the opposite effect in reverse, right? We'll have to eliminate 2 tons, and we'll only get 1 ton out of the atmosphere. So there are all sorts of these feedbacks that are complicated. It's not enough for me to say, we shouldn't be doing this. We need to stop. We need to have an endpoint for fossil fuel use. We have to accept that the aerosols do cool the planet a bit, and we're going to have to work extra hard to compensate for that.
Okay. Now let's talk a little bit about hydrogen. Now people say, well, wait a second, I thought you were talking about methane, but we are. So hydrogen is proposed as this great clean fuel, especially, right now it's made from methane. So it's really a fossil fuel. 95% of it's a fossil fuel, but there are ways to make it using renewable energy. And then you have this the hydrogen molecule, and it has a lot of energy. You can power cars and trucks and steel plants and everything. But there's a little side effect that people aren't aware of. Can you tell us what happens if hydrogen, not methane, if hydrogen leaks into the atmosphere, and what effect it has on climate?
Yeah, great question. Hydrogen is not itself a greenhouse gas. What hydrogen is the world's smallest molecule. So anytime we put hydrogen into a pipeline, if it leaks methane, it's going to leak more hydrogen. And hydrogen does other things to our pipelines we can talk about later. But hydrogen, although it isn't a direct greenhouse gas, it's what we call an indirect greenhouse gas because it lengthens methane's lifetime in the air. So the more hydrogen we emit to the atmosphere, the longer methane lasts. And you can think of it that that hydrogen consumes some of the cleansers or the natural detergents that are in the atmosphere, like OH, hydroxyl radicals. Those radicals would have destroyed methane, but they get consumed by the extra hydrogen in the air. And so hydrogen has an indirect global warming potential. I may get the numbers wrong, but it's like 12 times over a century. It's sort of in the 12 to 20 compared to CO2. So it's
pretty powerful.
And it is very powerful, and it acts almost exclusively through this interaction with methane. So we should be concerned about the development of a hydrogen economy. I have a chapter in my book on steel production where I really think the hydrogen use in that case makes a lot of sense. This is a company in Sweden, SSAB, that's producing the world's first green primary steel, starting with ore that is mined and eliminating all coal in the production. So they're using hydropower to make that hydrogen on site. So they're using clean electricity, not this steam reforming natural gas-based system that's, emits a lot of pollution and greenhouse gas emissions that produces more than 90% of our hydrogen around the world. They're using clean energy from hydro. They're consuming that hydrogen on site so they can monitor their operations, minimize leakage, and they're replacing all coal in their steel production. So it's a marvelous example of what can be done as long as there's a carbon price, right? They had to have a price on carbon dioxide pollution to get them over the hump to take the initiative to start that process, and it's happening today. So it's a fantastic example of what's possible when we price our pollution.
Go ahead.
I was just going to say, for hydrogen, maybe we can talk a bit about the hydrogen economy is coming. There's no doubt about that. And I think we could talk about whether we're discussing sort of concentrated industrial sources. I really like hydrogen for applications where you have, say, a blast furnace in steel, or you smelt cement production where you need a furnace at thousands of degrees. It's hard to do that with just sort of standard clean or green electricity. Where I get uneasy is when we start talking about putting the smallest molecule in the world in millions of cars through millions of pipelines. I've already said that everybody has a list of things that they like and don't like. I have concerns about the distributed hydrogen economy. I like hydrogen for large industrial sources, best of all.
Right.
But if our pipelines leak methane, which they do, they're going to leak even more hydrogen.
I by the way, 100% agree with you. And there's other problems with hydrogen in cars, is that you need 3 times more renewable energy to go a mile than you do if you just put it in a battery, because the whole efficiency chain of making hydrogen, compressing it, putting it in a car, going through a fuel cell, like 30% efficient, where a battery is like 90% efficient. So there's other reasons for staying away from hydrogen in those applications. But by the way, I want to congratulate you on your language. I interview a lot of climate scientists, and this is a pretty geeky program here where we like to dig into the real nitty gritty. But you're using words like detergent and cleansing instead of saying these radicals and whatever. And that's great, because you're speaking to the public, and you realize that the language that you use at Stanford is in your classroom is probably not the same language that the public could understand. So I just want to, I don't hear that very often. So I just wanted to congratulate you. Yeah.
Fine. Thank you, Dan.
And kind of speaking of that, in your book, you talk about, well, these are all the things we can do. And you just laid out for us at a high level. By the way, a link to the book is in the YouTube description there. You can go and learn more about it and get the book for yourself and get the details. But you said these are the approaches we can take, but we're also not doing them. And so you also talk about how do we go from where we are to where we need to be? And you talk about advocates and things. Can you just speak to that a little bit?
I can. There's so much that we're missing that we need to do. And in the United States, the first thing we need to do, I mentioned a few minutes ago, and that is to price greenhouse gas pollution. As long as it's free for companies to pollute the air, then almost anything we do bolted onto an existing operation costs more than not having it, right? So it's always, if pollution is free, almost any climate solution will cost more than free. In Europe, they've had a carbon price for decades, and that carbon price is generating innovation, like the steel plant I mentioned, production of wind turbines, and companies are changing their activities, and they're able to sell that technology globally and make products globally that people are demanding, low carbon products. So ultimately, I think we will definitely need a carbon price. That's happening at the state level to some extent in the US, but not federally, not yet. Then there are, the things that we can do individually. I chronicle a couple of advocates, people who just really impressed me. I went to see a guy, Mats Karstrom, who's a high school teacher. He devoted 40 years of his life to saving forests around him and had some national park-sized parcels of land set aside based on his activities to preserve the old growth forest there. He worked with hunters. He built coalitions of groups you might not expect to work together. Moose hunters who wanted habitats and helped him find rare species. He used rare species and taught his high school students to identify rare species that companies needed to protect if they were found. So he produced maps of endangered species and threatened species all over the area around him, and used that to put pressure on companies to save the old growth forest near them. And then I talk about a guy, Rev Yearwood, who started one of the founders of the Hip Hop Caucus, and the Hip Hop Caucus is all about climate, registration, voting rights, and they do a lot of work on disaster relief, hurricanes and things like that. So it's a terrific group, and as I interview him in the book, Rev talks about how he started going to rallies, and different types of people were going to rallies, but they all want the same thing, and that we need to work together to accomplish some of these things. So he's a source of inspiration for me too.
Well, that's great. I happened to be on a panel last weekend with a member of the Hip Hop Caucus, actually, talking about climate to musicians, actually, to try to get them more engaged. So you also, in your book, you talk about the need for environmental justice. And can you maybe, and it's kind of related a little bit to what you said, but can you maybe just expand on that a little bit?
Sure. I think everyone knows, and the scientific evidence is crystal clear, that poor people often, I don't like the term people of color, but that's a term that's widely used, that they breathe more pollution and suffer the consequences of pollution in ways that wealthier people don't on average. It's true in the United States, but it's just as crystal clear in Europe and elsewhere around the world too. So poor people pay the price or bear the brunt of pollution from all of our activities. And climate change provides an opportunity to sort of rectify that past injustice. So we want to make sure that the next set of technologies that we implement across the land are implemented more fairly to all people. And I see this in our work. We do a lot of work in my lab on indoor air pollution with gas stoves. And we measure not just the methane leakage from stoves, but the production of carcinogenic benzene and asthma-triggering nitrogen dioxide. And once again, poor people breathe dirtier air indoors as well as dirtier air outdoors. They live in areas where they can't necessarily open their window because the air outside is polluted. They may be renting, their appliances aren't as good, their vents aren't as good. They live in smaller quarters, so the same level of pollution results in a higher concentration that they breathe. So all over the world, poor people pay the price, and poor countries pay the price for our actions. And climate solutions have to address that issue, and in my opinion, and work to rectify it.
I want to go back to a question, maybe it should have been earlier, but we talked about reducing methane. What's your thoughts on systems to, I don't know, technologically reduce methane, like destroy methane, and also the same for CO2, like carbon capture? You had an opinion on solar radiation management, but what's your thoughts on carbon dioxide removal and methane? I guess methane eradication is the phrase instead of methane removal.
I have a whole section in my book that I call Drawdown. The first half of the book I call Emissions First, and that is emphasis on reducing emissions has to be the top priority today and almost forever. And then I have a section in the book called Drawdown Last, and that sort of summarizes my view that it's always more expensive to remove a gas from the air once it's already diluted into the atmosphere. If you take a leaking pen and there's a drop of ink on that pen, it's always less work to blot that ink with a tissue than it is to clean it out of your blue jeans or to remove it if it spreads into a glass of water or a swimming pool. So if we let a gas like methane or carbon dioxide go into the air and once we pull it out, it's like a needle in a haystack. We have to process a lot of air, identify that carbon dioxide or methane, latch onto it, and then do something with it. That will always be more expensive than keeping the gases from the air to start with. Carbon dioxide is becoming much more mainstream, CO2 removal. There are many startups and companies working in that space.
Absolutely.
I think we'll need it because of this extra trillion tons floating around the air. We can't deal with it in any other way. What we don't talk about is the cost. We don't talk about who's going to pay $100 or $500 or even $1,000 a ton to remove carbon dioxide from the air. If we weren't willing to pay $5, $10, or $50 a ton today, why should we expect the next generation to pay $500 just because we think it would be a good idea? So we don't talk enough about who pays for this carbon removal. And then finally, methane is even harder, right? It's more dilute in the air, a couple parts per million instead of 420 parts per million. It's harder to latch onto. It's a more difficult molecule to grab and crack open, especially at room temperatures. So we don't have the same amines or hydroxides that scrub carbon dioxide from the air like in a submarine. There aren't chemicals that do that yet for methane. So I work on methane removal and believe that we should be considering it and trying to develop technologies to do it, but it will always be more expensive and less desirable than stopping emissions.
Okay. Yeah, my thought on that is that, well, not getting rid of, well, focus on CO2, not getting rid of the CO2 is far more expensive than getting rid of it, even if it is expensive. I agree with you that getting rid of the emissions is the cheapest thing, but there's no reason we can't do both. But
it isn't. But just sorry to jump back in, but if you think about what are we doing today, we're removing a few million tons of carbon dioxide from the air, and I think those few million tons are important because it's helping establish an industry and technologies. But that is crazy if we're still allowing smokestacks to emit 10% carbon dioxide to the air and not capturing that CO2 at a far higher concentration.
No, absolutely.
It isn't
one cement plant puts out 1 million tons or more a year. One cement plant, and we have a long way to go. But your book's going to help make people more aware of what our choices are here, and like I said, it's a little unusual you coming on because you actually have an optimistic story to tell, which is unusual in the climate world. So I thank you for that. I'm going to open it up now to our co-mods. It's Stacy, and she could have her own question, and she might have some from YouTube Live as well. So welcome, Stacy.
Okay.
Hi, thanks for being here, Rob. So I'm like the every person. I'm not a climate scientist. I'm not an investor in climate tech. And I've been doing this with Dan for over 3 years. And I just learned today that hydrogen helps to keep methane around longer. Okay. That is why, what do you think of California's love affair with hydrogen-powered vehicles?
Well, I think the vehicle wars have been won by EVs, right? So there are only two hydrogen cars sold commercially in the U.S. today, and there are less than 20,000 vehicles or 50,000 vehicles sold, hydrogen vehicles of all time.
I should have clarified. Yes, I do. I totally agree with you on cars. That's kind of over. Trains. They're trying to make all of our high-speed trains, California, hydrogen-powered trains.
I hadn't heard about that. Okay.
I actually don't know anything about hydrogen-powered trains, so I'm reluctant to comment. But one way or another, electrifying the train system is an important thing that's happening in California and elsewhere, but it needs to happen. I don't know about hydrogen-powered trains, to be perfectly honest.
Germany has abandoned them. because it's just a boondoggle. But for some reason, California State Transportation Agency is fixated on hydrogen powered trains. And I just am baffled by it.
So say any other questions from YouTube that we should cover? Or
I hadn't seen them, but I did wonder if you do analysis of governmental policies in terms of what is the carbon footprint of that policy.
I do personally, and my lab does a lot of work on different policies. We work with state agencies trying to provide information. We work with, federal agencies like the EPA and, Department of Energy. So the Government Accounting Office sometimes asks for help trying to understand the consequences of different activities. So I do, yes. But I am somewhat old school in the sense of I was trained to do research that's policy relevant, but not policy prescriptive, if that makes sense to listeners. I'm trying to provide good information, but I don't often go out and advocate for a particular bill or push a bill unless I feel strongly about. What I have been working with a bit is the labeling bill for gas stoves in California, because we measure the direct pollution that the bill talks about. So the bill's signers came to me and said, what do you think of this? And so I gave them some feedback on that bill. So I will respond, but I don't normally initiate, if that makes sense.
Right. So then off of that, so do you think that the GAO should have that when they're or any level of government, when here's the policy and here's what it will cost to implement this policy, and here's the carbon associated with that policy as well? Do you think that would be helpful? Or
the agencies want good information. The agencies, EPA as an example, in my opinion, is slow to change, and it's hard to get the newest information into those agencies and have people include it and act upon it. So I think as scientists, each of us has to make a decision about how much time we're willing to spend to try and reach out to people beyond academia. I have always enjoyed doing that, and the later in my career that I get, the more willing I am to try and do that, to help people make things better beyond just publishing my papers and work. But that's a personal decision that each individual has to make.
And then the last one would be, have you analyzed Stanford and the carbon footprints of the institution and the practices of the university?
I'm working with Stanford on a couple of projects currently. So yes, I'm working with Stanford Dining to try and reduce emissions from the production, from cooking and the consumption of food. I have a graduate student in particular, Sierra Castaneda, who's working with Stanford Dining on that. We're working with them to electrify their kitchens. What it would take to get Stanford kitchens off gas and onto induction and cleaner electricity. And I just joined a committee to think about how Stanford has decarbonized most of its operations for electricity, but Stanford owns the land that a couple of thousand homes are on, including the home that I live in. I own the house, but I don't own the land. I lease the land from Stanford. So Stanford's starting to think about its Scope 3 emissions, and I'm working with this committee to quantify those emissions and think about incentives to electrify the leaseholders that Stanford is responsible for in their Scope 3 emissions. And then I have worked with Stanford in fossil fuel use more broadly and their sustainability committee.
Okay.
Will you?
I want to jump in on a question on Stanford, because the sustainability school had a big controversy about whether it's going to accept donations from fossil fuel companies. What's the status of that? I know that was going back and forth for a while.
It's been a very complicated issue for people in the climate space. You might ask, why is this a complicated issue? The reason it's a complicated issue on a college campus, at least on our college campus, is there are many faculty members who don't agree on the role of fossil fuel companies in the clean energy transition. And there are faculty who believe that large companies, like the ExxonMobils, the Chevron, whoever's on your list, the BPs, the Shells, we need them to scale climate solutions. There are people who genuinely believe that. There are other people who feel strongly that a subset of a university's faculty or students should not ever be allowed to tell a faculty member who they can work with. So if a faculty member, works with a Saudi Aramco, for instance, just as an example, that it's not that it is against academic freedom for a person like myself or even the university to say you may not work with a given person or a given company. That becomes an academic freedom issue, and nothing grinds action to a halt faster on a university campus than the perception that it affects academic freedom.
Wow. Well, by the way, that sounds like that's a great hour-long program to go into. Thanks for that brief description there. Stacey, I have something from Brian coming up. Do you have something else?
Okay, yeah. No, I was just in terms of Stanford and all universities and their admissions policies. You're talking about scope 3 emissions. Who you admit and how they get to school is a scope 3 emission that we just don't even no one considers. And I don't know if you have an opinion on that at all. Or
Well, I mean, one of the largest sources of scope 3 emissions for a place like Stanford would be student travel.
Yeah.
But I don't personally know how to tackle that from a Stanford admissions perspective. You wouldn't want to take your student body all from the 10-mile radius around the university to minimize that footprint. So I think there are big things that we can worry about now, and there are other things that may be big, but are sort of farther out on the edge. I like to think about focusing on those ones closest to the bullseye, and some scope 3 emissions are things we can tackle, and others are very hard, and maybe tackled by someone else, to be quite honest.
Or tackle it by doing what you said in your book. I mean, doing it not at Stanford level, but do it countrywide, globally,
And I do want to say Stanford's not perfect, but the operations team has done a lot to eliminate gas use, to use as much clean electricity as possible. We have a great sort of heat recapture and energy efficiency plant on campus. So hats off to the sustainability office and the operations here at Stanford. They've done a really good job.
Great.
Okay. Thanks.
Thanks, Stacey. Yeah. And Brian, welcome to Climate Chat.
Yes. Thank you, Dan. And Rob, great to hear your thing. I've got a two-part question for you. The first is about polar emissions, and the second is about OH radicals. On the polar emissions, I was astonished to hear about methane pit crater in Siberia, first discovered in 2014, doubling every year after that, to the point where over 1,000 pit craters have been identified in the Siberian tundra in the past 7 or 8 years. And then furthermore, the subsea permafrost, there's over 1,000 gigatons of carbon locked up in shallow seas. And of course, we know ocean warming is on a superlinear trajectory. So we're worried about, is that 100 times worse than the greenhouse gases we have in the atmosphere today? Second part is OH radical.
Let's do that one at a time, little man. The first question there about.
Okay, so there were two. One was the burst craters that have shown up in Siberia, Yakutsk, and such. So I don't know much about these, but these are craters that are, 150 feet wide, 50 meters wide. 50 meters deep in some cases, 20 meters wide. They're just appearing in the middle of nowhere. No one completely understands how they're formed. It appears to be pressure that's built up, perhaps from methane gas that's thawing and puddling underground and blasting these burst craters into the air. But we really don't understand them very well, and they're in distant, isolated environments. They're hard to study. They pop up randomly. So it's kind of a mystery. The BBC likes to cover burst craters. And then you're absolutely right about especially shallow sea. Dan mentioned clathrates earlier. Permafrost. It's a huge concern, not just on land that I mentioned earlier, but on shallow sea floors and in the ocean too. And it's like putting the genie back in the bottle. If we start to liberate those gases, free up that methane, as long as it makes it through the water column. If the methane's released in the deep ocean, the methane doesn't reach the air as methane because it's oxidized on the way up. But in shallow seas, shallow coastal areas in particular, like off Siberia, that methane bubbles up into the air. Really, really bad news.
Okay.
Yeah.
And your second question, Brian?
Second question is OH radicals. You did a good job of describing the more OH radicals we have in the atmosphere, the more methane scavenging and accelerated drawdown we have of that methane in the atmosphere. What blew me away is the critical role of aerosols to actually facilitate that surface chemistry reaction. And the fact that we've cut aerosols so much recently, it seems like a hidden thing that people aren't talking about. In other words, less aerosol surface area, less OH radical conversion. And finally, your thoughts on more active OH radical or other kinds of methane scavenging that we might consider as a catalytic, call it methane oxidation in the atmosphere. I'd love to get your input on both of those.
Yeah, really, really excellent question. I would say that there are two of the largest uncertainties in the global methane budget, in my opinion, and we release a global methane budget. We're about to release a new one in a month or two. The two largest ones are uncertainties around natural emissions from wetlands and freshwater systems. And the other one is the sink side of the equation, how much methane is destroyed and sort of how. The best tracer that we had in the past is a gas called methylchloroform, and that is going away because of interactions with pollution and CFC reductions. And so we're losing the tracer that we use to estimate OH abundance. OH radicals are hard to study. They only last about a second or so in the air.
Oh.
So they form quickly. They don't last long. So they're hard to study, hard to model. They're complicated. Very hard for me to imagine generating OH radicals at a scale that would be meaningful in the open atmosphere. Chlorine might be different. It lasts longer and has more of a catalytic effect. But you have to, if you think of something lasting just seconds, literally, you just have to keep pumping those OH radicals out constantly to have an effect. And I don't see that as being likely to be effective. It might work in a closed system, like in a reactor unit, and not might, it could work in a closed system. But in the open air, we can't really manufacture hydroxyl radicals at a scale that will be meaningful, in my opinion. I'm not sure if that was your question or not.
Yeah, there is actually an exception there, and that is there's plenty of chlorine in the sea and sea spray, and there's a very interesting chlorine surface chemistry that takes place that ends up catalytically producing OH radicals on the surface of aerosols. So this is something we've really got to dive into, and that is surface chemistry, because we've just cut our aerosols by a huge factor. And if we've now also cut our methane oxidation by a huge factor, that's a big problem. And I think it's something that I'd love to get your thoughts on as we go forward.
Yeah. Well, I did take chlorine out of the answer that I gave just a minute ago, and chlorine has some advantages in several ways. It's more powerful at destroying methane than OH is. It lasts longer, tends to have these catalytic effects. And there's a lot of work being done in the space. I'm out of Copenhagen, for instance, people trying to understand these mechanisms. So yeah, I guess I'm agreeing with you, Brian, that we need to study them more, and there may be some technologies that we can develop around that chlorine interaction.
By the way,
Dr. Franz in Germany is an expert on this, and he said that the chlorine surface chemistry that comes from the sea spray actually has a profound catalytic effect on OH radical abundance, and it's tightly related to aerosols because that's where most of the surface area is for these interactions. So I recommend Dr. Franz's Healthy Planet Action Coalition.
Okay.
And I believe you were mentioning Copenhagen. That's my brother in Copenhagen is working with ambient carbon, one of the companies working on that. We actually I interviewed him long ago on back when it was Clubhouse, not YouTube, so that's not available right now. So, Rob, thank you so much for a clear and somewhat optimistic discussion. I mean, a lot of work to go. We all have a lot of work to go. I mean, if we had more time, I would just really just focus on how do we get to where you want to go. You did talk a little bit about advocates and things like that, and that's so important. We have a lot of work to do, I think, on that, getting the word out. But your book is helping with that. Again, I think you do a great job in communicating with the public. You should get out more. There's not enough climate scientists with that. I mean, Catherine Hayhoe, which we'll have on in a few weeks, she's kind of well known for that as well. But It's not a very big list, but thank you so much for the work you're doing. Maybe you could just, the last question is, what's your current research that you're working on that you're excited about that we're going to hear about maybe in a little while?
Yeah, first of all, hats off to people like Catherine Hayhoe. She's a master. I mentioned I'm working with collaborators in many countries to establish a methane monitoring network across the Amazon and into Africa.
Mm-hmm.
I enjoy that work, so I'm excited about that. I continue to work on emissions from homes and buildings in the nexus, the intersection of reducing greenhouse gas emissions and making us healthier. Because as our air outdoors becomes cleaner and cleaner, the pollution we breathe indoors becomes more and more important in our lives. And if you're using a gas stove currently and you have the means to swap it out, you should swap your gas stove for an induction stove today if you can. And I'm happy to provide references for why I say that, not just for climate, but for the pollution that you breathe and your family breathes. So I continue to do that work and many other things on the methane cycle. I'm leaving for Sweden in a week or so to study old growth forests there that are more sort of carbon dioxide and diversity related, not so much methane. The benefits of leaving some forest stands in place rather than cutting them for biomass, for instance, and how to improve restoration of forest plots.
Great. Well, thanks for the work you're doing. Thanks for also spending some of your time with your outreach activities like writing this book. Again, link in the description to access more in the book. And also, there's also a link to your Stanford profile and things like that for anyone who wants to learn more about you and what you're doing. Right. Rob, thank you so much for being here on Climate Chat today. We really appreciate the discussion.
Thanks for having me, Dan, and thanks to all the listeners for your questions. And the book is about optimism and climate repair. So don't give up, keep the faith. Intotheclear.com, and thank you for all your work.
Thanks. Take care. Bye, everyone.